In this class, we're going to leave tensile testing and compression testing behind, and we're going to start a new section of the course. And I have to tell you, I enjoy the entire course. I really do. I think this is a very interesting course. It's fun for me to teach. I really enjoy it. But in all honesty, I really do enjoy this next section of the course the most, if I'm being honest. Lab 7 is a lot of fun. Lab 7 builds off of what we're going to start talking about today, which is heat treatment. So we're actually going to do some heat treatment on a bunch of different steel specimens. That's the first part of Lab 7. And the second part of Lab 7 is we're going to take those heat-treated specimens, which we have applied different heat treatments to, and we'll take that into the lab and we'll do some impact testing. And you probably don't know what that means quite yet, but we'll talk more about it in the next week or two. Basically, we're going to break them, and we're going to see how much energy they absorb when they break. The other cool thing about Lab 7 is we're going to use liquid nitrogen, because interesting things happen to materials, pretty much all materials, when they get below a certain temperature. And we'll talk about what that certain temperature is. There's a name for it. And we'll talk about that some more in the coming week or two. But that's pretty fun. We'll have to take our precautions with liquid nitrogen because it is extremely cold. So you'll have to wear gloves and you'll have to use tongs to move the specimens around once they've been submerged in liquid nitrogen, because you don't want to be sticking your hand into a bucket of liquid nitrogen. That's a good way to have your fingers fall off, literally. So we don't want that to happen to anybody. So we'll take the appropriate precautions with liquid nitrogen, but it's pretty fun. It's very entertaining to work with. And after everyone has done Lab 7, we'll have liquid nitrogen left over. So it's always fun to play around a little bit with some liquid nitrogen. I like to freeze apple cores and orange peels, and marshmallows are really good. So we'll talk more about that in the coming weeks. But so that's Lab 7. And then in Lab 8, we'll start talking about beam bending. So this is like a beam that we apply a load to, and it's going to bend. So we'll talk about beams and how much they're going to bend and how much load they can support and things like that. And in Lab 8, in your groups, you're going to design and build a beam. I'll give you some specifications and parameters that you have to adhere to, but you can use your creativity and you can design whatever kind of beam you want to. And you'll come into the lab and you'll build your beam out of wood and glue, different kinds of wood, whatever kind of wood you want. And we'll let it dry. And then in the next day for Lab 8, we'll go down to the lab with the Instron machine, and we'll test all of your beams. We'll break them, and we'll see how much force it takes to break them. So Lab 8 has some extra credit opportunities. I like to give some extra credit in two different ways for Lab 8. First of all, I'm going to give some extra credit to whoever can design the strongest beam. So if your group has the beam that is the strongest and can support the most force before it breaks, then I'll give some extra credit to that group. Also, we're going to talk about predicting and calculating how much force beams can support. So the group that most accurately predicts how much force their beam can support before it breaks, I'll give that group some extra credit as well. So there are some extra credit opportunities coming up. There's actually one for Lab 7 as well. I'll talk more about that when we get closer to that time. So there are some extra credit opportunities in Lab 7 as well as in Lab 8. Lab 9 is fun too. It's about shear stress and shear forces. We'll talk more about that in a month or so. But starting today, we're going to talk about heat treatment. That is the topic for today. And you'll observe that as we talk about it today, most of what we're going to talk about is directly applicable to steel. We're going to talk about different phases of steel and heat treatment of steel. But what I want to say at the very beginning is that this is actually applicable. The principles are applicable for any type of metal alloy. So that means if it's an alloy, it's not a pure metal, right? And we know that steel is not a pure metal. Steel is not pure iron. It has carbon in it. And if it was pure iron, you couldn't heat treat it. Same thing goes for aluminum. You can heat treat aluminum alloys, which is mostly what you work with when you're working with aluminum. You just can't heat treat pure aluminum. If it's pure aluminum, it's not going to work for heat treating. So heat treatment kind of has to do with the mix-ins, the alloying materials, which primarily for steel is carbon, but for other materials like aluminum, it could be other things. It could be other alloying elements. So the diagrams that I show today would look different for different type of materials. Like for aluminum, the phase diagram would look different for aluminum, but the same types of principles would apply. So you're learning about heat treatment of steel in today's class and in the next couple of class sessions, but really you're learning about heat treatment principles that are applicable to lots of different metal alloys. Okay, so I just want to point that out beforehand. So we can change the material properties by heat treatment. We can change the properties. We can make things softer or harder or stronger or more ductile or weaker. We can change a lot of those material properties by heat treatment, by doing different kinds of heat treatment that we're going to talk about today. Now, there are compromises and trade-offs. You know, for example, if you take a specimen and you harden it, you apply a hardening treatment to it, well, it's probably also going to make it more brittle. So there are some kind of side effects that go along with these, but we can have quite a bit of control over the mechanical properties of our specimens by applying different kinds of heat treatment that we'll talk about later today and in the next couple of weeks. So let's go ahead and get started talking about heat treatment, and I'm going to switch over to my slides. All right, let's get started. Heat treatment of metals. All right, to start out, this is kind of a motivating slide. Let's say that you are designing Captain America's shield. And I don't know about you, but my family, we like to watch the Marvel series of movies. So we like Captain America. We like all of the Marvel action heroes. I hope I'm not messing that up. Captain America is Marvel, right? I don't know. I'm going to assume so. But anyway, let's say you want to design Captain America's shield. What properties, using words that you already know, we've talked about these different mechanical properties of materials, what would describe how you want the shield to behave, right? So it needs to be able to absorb or deflect or not break, right? Like as people are throwing rocks or shooting arrows or shooting guns or lasers or whatever at this shield. So you probably want this shield to be really strong, right? Because you don't want it to break. You want it to be able to stand a high amount of stress. So you want it to be strong. You probably don't want it to split, you know, when you shoot an arrow at it or something. So you probably want the arrow to just kind of deflect off of it and just kind of bounce off of it. So you probably want it to be hard, because if it's hard, then the arrow won't embed in it. It will just kind of deflect off of it. You probably want it to be really tough, right? Because you don't want it to just like shatter when somebody shoots a gun at it or something. So you want it to be very tough. If you want it to be tough, then you know you want the area under the stress strain curve. And if you want the area under the stress strain curve to be high, then not only must it be strong, but it has to be at least a little bit ductile, right? If you want it to be tough. All right, so we said we want it to be strong and hard, and what else did we say? Tough, and at least a little bit ductile, right? I suppose also we'd want it to be kind of lightweight. At least if I'm carrying this thing around, I want this to be lightweight. And I also want this thing to be fairly rigid. I don't want it to be all like wobbly, you know, like imagine this piece of sheet metal and you're like shaking it and it goes wah, 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 wah. You don't want it to be doing that. You want it to be fairly rigid. So let's see if we got some of these. So we want it to be very strong. We want it to be tough and hard and at least a little bit ductile and rigid and lightweight. Yeah, I think we said all of these. The terms over here that have an asterisk, that's hard to say, asterisk, after them are properties that we can change by doing heat treatment. So we're going to talk about these towards the end of this class session. We're going to talk about how you would change the materials by doing different heat treatment processes to make the materials more strong, tough, hard, or ductile. Some of those might be different heat treatment processes, but you can apply more than one heat treatment process to it. Rigid, so that rigidity is going to be given by the elastic modulus. Can't really change that. You're kind of stuck with whatever the elastic modulus of your base material is. Lightweight, same thing with density, which would affect the overall weight. Can't really change the density of the material by doing heat treatment on the material. Let's do one more example. What if you're designing a sword for a samurai? What types of mechanical properties would you want your sword to have? The first thing that comes to my mind is you want it to be hard, because if it's hard, you can sharpen it and it will hold its sharp edge if it's hard. What else? Well, you probably want it to be pretty tough because you don't want it to break, when you're hitting something with it. And if you want it to be tough, then once again, you want it to be at least moderately ductile. And you probably want it to be kind of strong as well. So, I'm thinking some of the same properties as we talked about before. Probably want to focus on the hardness, at least for the cutting edge though, so that you can sharpen it. And so it'll hold that sharp edge. And probably the same thing as before, I'd like this to be somewhat lightweight. Yeah, so we got most of these. Very hard, that's probably the most important thing. Very strong so that it doesn't fail when you hit something with it. And tough, we said. And yeah, if you want it to be tough, then it is going to need to be at least moderately ductile to get a high area under the curve. And you probably want it to be fairly rigid so it doesn't, flop or wobble. And you want it to be fairly lightweight if you're going to be carrying this thing around. And once again, the ones with the asterisks are the ones that we can change or control somewhat by applying different heat treatment processes. All right, so here's a roadmap, what we're going to talk about in this class today. There's a lot of material. I got to tell you ahead of time, there's a lot of material in this class today. There won't be as much in the next class session, so you can look forward to that. But yeah, there's quite a bit of stuff that we're going to talk about today. The first thing that we're going to talk about is called the steel equilibrium diagram. And this is kind of a map of all the different forms that steel can take. So you're probably up to this point, unless you've read or had some classes on this in the past, which most of you have not probably, you might be thinking of steel as a pretty homogeneous material. I mean, that would be a reasonable thing to do, to think of steel as being a homogeneous material. And even though we've said in the past that metals are made up of grains, right? So you know that. Still, you might be thinking that pretty much all those grains are the same. You've got steel, a steel piece that's made up of individual grains, but you might reasonably be thinking that all those grains are identical, or at least made up of the same type of stuff. As it turns out, it's not. As it turns out, steel at the microscopic level is a pretty heterogeneous material. And those grains can be quite different from one another. So we'll talk more about what those grains can look like. We call those phases, different phases of material. We'll talk about that in just a little bit. And then we'll talk about triple T, time, temperature, transformation diagrams. I think of these as kind of like the recipe. If you want to get a certain kind of steel with certain mechanical properties, this is kind of like the recipe. It's a pictorial recipe. So it's kind of like you follow the picture. You'll see what I mean when we get to it. But it's a diagram that tells you how you should apply a heat treatment, or how you should cool it down, or how quickly or how long you should take to cool it down. Yeah, we'll talk more about that. And then we'll finally get to our heat treatment processes. There's mainly 4 different types of heat treatment processes. These are the basic ones. So we're going to focus on these 4. There are more. You can definitely find other kinds of heat treatment processes, but these are the basic ones. So this is the last thing we'll talk about in this session, probably in the next video. We'll talk about hardening and tempering and normalizing and annealing. And all 4 of those things do different things and impart different mechanical properties to the metal. Okay, here is our phase equilibrium diagram. All right, so the easiest thing to think about, and by the way, this is only actually part of the equilibrium diagram. The easiest way to think about this is start with your molten liquid metal. It's really hot, right? So over here on the vertical axis, this is our temperature. And the horizontal axis, this is the percent carbon. Because as it turns out, how much carbon you have in your steel makes a big difference to how your grains form and what your grains look like, and therefore the mechanical properties of the steel overall. So let's think about this. We're up here, we have molten steel, all right? So we're in the liquid phase, which is actually not shown on this portion of the equilibrium diagram. And what we're going to do is we're going to gradually cool down the steel. And so we're going to cool it down below the melting temperature, so it's going to freeze. All right, so it's going to freeze, and the first form that the steel is going to take while it's really hot, look how hot this is going to be, like 21 degrees Fahrenheit, down to a lower amount of a little bit more than 1300. I'll tell you in a little bit, it's going to be, this line right here is 1333 degrees Fahrenheit. But anyway, the first form of solid steel, this is a solid, the first form of solid steel that you get is called austenite. Austenite is a form of steel that only forms at very high temperatures right after you cool it down enough to solidify it, freeze it, all right? But you don't have austenite at room temperature. The easiest way for me to describe the difference probably is if I tell you that austenite actually has a different lattice structure. Austenite actually has a face-centered cubic lattice structure, and when I cool it down even more, then we're going to get different structures that have different lattice structures. All right, but the first thing we get is austenite with an FCC lattice structure. As you cool it down some more, what you get depends on how much carbon you have mixed into the steel. So if you have low carbon, let's say like a 1040 steel or 1045 or something like that, technically I might say that's medium amount of carbon, but let's say it's about 1040, something like that. So 1040 is 0.4% carbon. So right here, we cool it down from a molten state, we get austenite, and then we cool it down some more. And this line right here, this curved line, is called the upper critical temperature, the upper critical temperature. And you can see this line is not horizontal, so it depends on the amount of carbon that you have. It has a slope to it. But when you cross that line, some of your austenite transforms from a form of austenite, which has FCC structure, to a different grain structure, which we call ferrite. Ferrite is a grain structure that has a BCC, body-centered cubic lattice structure, which has a pretty big impact, actually, on the mechanical properties. So in this region right here, between the upper critical temperature and what we call the lower critical temperature, you have both phases. You have austenite and ferrite coexisting in the material. Some of the austenite grains have been transformed into ferrite, but not all of them. And as you cool down closer to the lower critical temperature, which is horizontal at a constant, it's 1333 degrees Fahrenheit. As you cool down closer to this horizontal line, lower critical temperature, more and more of your austenite grains get converted into ferrite grains. And once you go below the lower critical temperature, then you have converted all of your austenite grains into grains that are either ferrite, which we'll talk more about these in a little bit. Don't worry. We'll talk more about austenite and ferrite. And the other thing that you can get, the type of grain, when you have a relatively low carbon content in this region right here, ferrite and perlite. We'll talk more about perlite grains in a little bit. As long as you are below about 0.8% carbon, so 1080 steel, as long as you're 1080 steel or below, like 1040 or whatever, then your grains in your steel at room temperature, at temperatures below the lower critical temperature, all those grains are going to be either ferrite or perlite. All right. The other thing that we'll talk about is up here with a higher carbon content. Let's say you got, let's take like a 1095. So that's a pretty high carbon. So that's going to be about right here. So I cool it down from the molten state and I form austenite just like before. And then I keep on cooling it down and I'm going to cross the upper critical temperature. And notice I'm trying to come straight down vertically because my carbon content is at 0.95%. So I'm coming straight down vertically. So I convert my austenite here into cementite. And cementite is a different grain structure. We'll talk more about what cementite is. Technically, it's actually a ceramic material. But we'll talk more about that. And then in this region right here, the tan, you have both austenite and cementite coexisting. And then if you cool down even more below the lower critical temperature, then in this region, below 1333 degrees Fahrenheit, down to, basically as low as you can go, you have cementite grains and perlite grains coexisting in the material. All right, so that's how to read this. You can tell what form your steel is at. We should say phase. Let's say what phase your steel is at if you know the temperature that your steel is at and the percent carbon that your steel has. So you'll know what grain structures are in your steel by knowing those two things. All right, so here's a little bit of motivation and explanation for the way some of this can happen. All right, so think back to when we were talking about grain formation. You've got a liquid, and then you cool it down below the freezing temperature, and it starts to freeze, right? But the thing is that we know this. We've talked about this before. The freezing doesn't happen like that. It's not like, boom, you fall slightly below the freezing temperature and boom, all of a sudden your material is entirely solid. No, it doesn't work like that. Freezing is a process that takes time. It takes a finite amount of time. It's not just like an instant thing that happens. So we know that we form grains. The grains begin to form at what are called nucleation sites or inception sites, either one. I may have used inception sites before, but same thing. And what happens is the lattice structures, think about these three-dimensional lattice structures. They form at a nucleation site, which is usually an imperfection in the material, in the mold that you're using. So there's an imperfection there, and then that cools down a little bit faster. So that's where it starts to form the grain structure. And then once it starts to form, it gradually grows outward and builds its lattice structure. And that's happening at multiple points, multiple inception or nucleation sites. And all these grains begin to form from different nucleation sites, and they grow together and they form grain boundaries. All right. So there's definitely a time when both solid and liquid exists in the material simultaneously. It's like if you go to Dairy Queen and get a slushie, or I guess like 7-Eleven, and you get a Slurpee. That's what they call them, right? A Slurpee. Yeah. So a slushie or a Slurpee is basically it's this. It's a substance where ice and liquid, solid and liquid, exists at the same time in the same material. So that's kind of the same way that metal acts when it's freezing too. You got a period of time when you've got like a slushy, a slushy with a solid and liquid metal. All right, so more generally, it's also true that you can have different types of grains in the material at the same time. So not only can you have multiple phases, like solid and liquid, in the material at the same time, but you can actually have different grains. Like you can have ferrite and perlite, or perlite and cementite, or austenite and ferrite, or austenite and cementite. You can have different grain structures in the material at the same time, just like you can have different phases of matter, solid and liquid, at the same time. All right, so like I said before, steel is usually not a homogeneous mixture. You know, probably for most people coming into this class, they might assume that steel is this totally homogeneous mixture. Maybe they know that it's iron and carbon, maybe, but they might just think that it's this like constant material, and you zoom in on it and you'll just see iron and carbon atoms. Now in the first third or 2/3 of the semester, we talked about grains, so you know about grains now. But now we're making it a little bit more realistic, and we're saying, well, you know those grains that we talked about? Those grains are not all the same. So those grains are not homogeneous. You might have a ferrite grain right next to a perlite grain, and then the one next to that is another ferrite grain. Or different material, you might have perlite grain right next to some cementites, and then on the other side of that you have another perlite grain, and these are all grain structures that are growing together. All right, so steel is a pretty heterogeneous material when you zoom in on it to a microscopic molecular level. All right, so we have different microstructures, and by that I mean different lattice structures. All right, you can think of it that way. We have different lattice structures that the steel takes the form of, depending on how much carbon it has and its temperature. Kind of interesting, isn't it, that you can change from an FCC lattice structure to a BCC lattice structure just by changing the temperature? But it's actually true. Austenite, with really high temperatures, right after it solidifies from liquid, austenite is an FCC lattice structure. And then as you cool down more and you form ferrite, ferrite is a BCC lattice structure. The important thing to know about that, the most important thing to know about that, is that FCC lattice structures can absorb a whole lot more carbon because they have a whole lot more interstitial locations. That's not obvious, but it's true. If you have iron in an FCC lattice structure like austenite, it can absorb and it can hold a whole lot more carbon in the interstitial locations than a BCC lattice structure made from iron can. All right, so the question is, where's that carbon going to go? And that's a very important question as we talk about these lattice structures and these different grain structures for steel as it's cooling down. All right, so we have austenite that can hold a lot of carbon, and then it's going to cool down. That austenite is going to change form into ferrite and other things. And ferrite has a BCC lattice structure, can't hold all that carbon, and so it has to go somewhere else. The carbon has to go somewhere else. Okay. All right, so the different phases or we'll say phases or microstructures of steel kind of mean the same thing. We're going to talk about ferrite and perlite and cementite. These are the ones that we're going to call equilibrium phases. These are equilibrium phases. I may as well say this now. What do I mean by equilibrium phase? An equilibrium phase means that it will form if you allow the cooling to happen slowly. All right, so if you allow this to happen via a very slow process, you will reach what are called equilibrium phases. If you take this cool down process and you speed it up, which is going to require some artificial intervention, you know, you're gonna do what we call quenching it in cold water or oil or something, or even cold air. If you quench it, you're not going to form an equilibrium phase, because equilibrium Equilibrium phases require a slow process. The important thing about that is when you do it slowly, you allow the carbon to naturally migrate, or we're going to say diffuse from one grain to another, and you're allowing the carbon to naturally move where it needs to go. If you do it quickly, if you quench the material really quickly in water or oil or even cold air, then what's going to happen is you're going to actually freeze the carbon in its position. We'll talk more about that later. I don't want to get ahead of myself. But for right now, we're going to say that ferrite, perlite, cementite, these are equilibrium phases. Austenite is also an equilibrium phase, but it only occurs at high temperatures. You already know that because you already saw the picture that I showed before. These last two are not equilibrium phases because they require rapid cool down. You have to really cool down the steel really fast if you want to form these. And we'll talk about these last, all right? So we're not going to talk about these quite yet. All right, so here is a little bit more of the phase equilibrium diagram. I only showed you about this, the lower left portion of this diagram previously. But now this is a more complete phase equilibrium diagram for steel. What we've got up here is the liquid phase. Conveniently, L stands for liquid. So this is liquid molten steel. As you cool it down, you're going to get what's called gamma phase, which is austenite. All right. So when you see the gamma, this is a gamma right here, a Greek letter gamma. It kind of looks like a Y. It's kind of a funny way of writing a gamma, but this is a Greek letter gamma. And gamma is shorthand. Don't ask me why they did this, but gamma is commonly shorthand for austenite grain structure. All right, so when you first start cooling it down, you get a combination, like a slushy, of gamma, austenite, and liquid molten metal. All right. As you continue to cool it down, you get fully solid material. This is all austenite in this region right here. I know you can't see my pointer real well because my pointer is red, so I can't point out this region very well, but this is austenite right here. And then like before, here is our upper critical temperature, which varies depending on the carbon content. And here is our lower critical temperature, which is horizontal and a consistent 1333 degrees Fahrenheit. And then below that, depending on how much carbon you have, you'll either get all ferrite and perlite grains, or if you have more than about 0.8% carbon, you're going to get all perlite and cementite grains over here. All right. What else can I point out? I'll point out this region up here where you have a different phase. You have what's called delta phase iron. And basically, I'm going to tell you it's not important. We're not going to worry about delta phase iron or delta phase steel. It's way up here at very high temperatures and very low carbon content. So for practical purposes, it doesn't really matter. You know, when's the next time you're going to use steel that is, you know, less than 0.1% carbon and approximately 2,700 degrees Fahrenheit? Probably not going to happen. I've never seen with my own eyes even delta phase iron. So it's not very important. So that's what these are. This is where you got delta phase and liquid. This is down here is where you got delta and gamma. So you got delta steel as well as austenite. And they're small regions and they're very high temperatures and very low carbon. So they're not really that important. Over here in this region on the far right is not very important to our current discussion. It is relevant to cast iron because this is cast iron over here. So this is a phase equilibrium diagram that includes cast iron. It includes some of the same things. You can see that the only additional thing is this funny looking word called ledeburite. And ledeburite is a phase of steel that acts a lot like cementite. It's very hard and it's very strong, but also very brittle. All right, so the area that I want you to focus on and I want you to know is this region right here, all the way from liquid, ignoring the delta phase stuff over here, the liquid stuff down to austenite, and in this region right here. Actually, let me point out one more thing. There's a little sliver over here that's called alpha phase steel. And in alpha phase steel, it's purely ferrite. It's only ferrite. Whereas over here in this region, you got ferrite and perlite. But if you have really low carbon content, then you can get pure ferrite. But the thing about ferrite, I mentioned this before, but let me say it again. Ferrite is a BCC lattice structure, and it cannot hold very much carbon at all. Very low solubility for carbon in ferrite, the BCC structure of ferrite. So if you're in this region, that carbon has to go somewhere. It can't be absorbed by the ferrite, and so it forms, through diffusion of the carbon, it forms a different phase called perlite, which we'll talk about in just a couple of slides. But if you don't have very much carbon at all, then the carbon can be absorbed by the ferrite grains, and therefore you just have ferrite grains. So over here in this kind of dark yellow region, you have an alpha. This is alpha steel, and it is purely ferrite, just ferrite. If you have more than that, you have perlite and ferrite. And if you have more than that, you have perlite and cementite at room temperature. All right, a little bit more about austenite. It's an FCC structure. It exists only above the lower critical temperature. In fact, if I go back, so you'll see in this region over here, I still have some austenite and cementite. And over here in this region, I have alpha, which is ferrite, plus austenite. So there is no austenite below the lower critical temperature, which is right here. Okay, so austenite exists only above the lower critical temperature. And some of the austenite starts to be converted to different types of grains when you get below the upper critical temperature. But definitely none of it exists below the lower critical temperature. All right, so as it's cooling from austenite to something else, if it has less than about 0.8% carbon, it will turn into a combination of some ferrite grains and some perlite grains. If it has more than about 0.8% carbon, up to about 2% carbon, then it's going to form a combination of perlite grains and cementite. And if it cools really quickly, we'll talk about this last, it's going to form a non-equilibrium phase that we call, could form martensite or it could form bainite, depending on how quickly you quench it or cool it down. All right, so this is what I've been saying. If you have less than about 0.8% carbon, you cool it down. And when you're down to room temperature, way down here, then you will form perlite and ferrite grains. And if you're above 0.8% carbon, when you cool it down, you're going to form perlite and cementite grains. Okay, all right, let's talk about ferrite a little bit. Ferrite has a BCC structure. Carbon is not very soluble. It can't be absorbed by the ferrite BCC structure. It's only about 0.02% carbon that the ferrite BCC structure can actually absorb and hold in its interstitial locations. Ferrite grains tend to be relatively soft and ductile. This is also what gives steel or iron its magnetic properties. Magnetism is actually a pretty complex subject, and it's heavily dependent on the lattice structure. Interestingly, austenite with an FCC lattice structure at high temperatures is actually not magnetic, which is pretty interesting. But when you cool it down and you form a BCC structure, it is a magnetic material. You will only get ferrite grains. You'll only get ferrite grains when you have less than 0.8% carbon. If you have more than that, you will not have any ferrite grains. If you have a low carbon steel, like say 1018, like we've been working with, most of the grains in 1018 steel or any low carbon steel, most of the grains are ferrite, and you'll have a few perlite grains mixed in there. If you're in this range between 0.02% carbon and less than 0.8% carbon, and you're less than 1333 degrees Fahrenheit, the lower critical temperature, then all of your grains in your steel will be either ferrite or perlite. As you get closer to 0.8%, then you're going to get more and more perlite grains and fewer ferrite grains. Conversely, as you get lower and lower carbon content, the lower the carbon content, the more ferrite grains you get and the fewer perlite grains you get. Here's what it looks like under a microscope. They look like little rocks, gravel. All right, so if you have more carbon than can be absorbed by the BCC structure in ferrite, which is more than 0.02%. So if you have more carbon than that, then as it's cooling, the carbon has to go somewhere. It has to do something because it can't be absorbed by the ferrite. And where it goes into this new grain structure called perlite. Perlite tends to be stronger, but it's less ductile. And that's because perlite contains layers, and some of those layers are actually something called cementite. And cementite is a very hard, very strong, but very brittle material. So perlite grains themselves are harder and stronger than ferrite, but not as hard or strong as pure cementite, which we'll talk about in a little bit. All right. So what you really see when these are real pictures. These are real pictures right here. You see these alternating bands, and what these alternating bands are, where the light colors are, let's say right here. So these light colors right here are actually ferrite, and the bands in between them, the dark colored bands, that's actually cementite. And I suppose, you know, a long time ago, they couldn't quite zoom in with the microscopes quite close enough to see these. And if you don't zoom in all that closely, then it's hard to see these alternating bands. The whole grain just looks kind of grayish in color if you don't zoom in close enough. And so that's actually how it got its name perlite, because it's not as light in color as ferrite is. It's a little bit grayer. And so it looked like kind of mother of pearl, I guess. And so that's why they named it perlite. All right. So relating back to what we talked about a few minutes ago, as you get closer to 0.8%, you're going to get more and more perlite grains and fewer ferrite grains. As you go above 0.8% carbon at room temperature, you're going to get perlite grains, but also you're going to start getting more and more cementite, pure cementite, not in a perlite grain. The thickness ratio here, I said these have alternating bands of ferrite and cementite. The thickness ratio is always 8:1. The thickness of the ferrite is 8 units compared to the band of cementite is 1 unit. So it's always an 8:1 thickness ratio. And the perlite grains themselves, one individual grain of perlite is always 0.8% carbon. So by extension, if you have a steel that is, say, 1080 steel, so that steel is 0.8% carbon, then that steel grain structure is entirely perlite. It's all perlite because there's just enough steel, so just enough carbon so you don't have any ferrite, but not enough carbon to where you start getting excess cementite. All right, I think I've said all of this. Okay, so we're talking about high carbon steel now. When you cool it down below the upper critical temperature, you get austenite and cementite. And when you keep cooling it down, you form perlite, which we talked about, and cementite. So let's talk about cementite. So cementite is actually iron carbide. It's a covalent bond between the iron and the carbon. So it's not like the carbon is just hanging out in the interstitial locations of, you know, a BCC structure or an FCC structure. This is actually a covalent bond between the iron and the carbon. It's actually a ceramic, like I said, and it's a very hard and very brittle material. So the more cementite you have in your steel, the stronger and the harder and the more brittle your steel is going to be. The lattice structure is pretty complicated. Here's a picture of the lattice structure. Don't even try to make sense of that. But it is an orthorhombic lattice structure. So it's not a simple lattice structure. And of course, like we've talked about, as you get more and more carbon above 0.8%, you get more and more cementite and less perlite. Okay, there is a very important point here called the eutectic point. You can probably see right here that this area right here has a lot of stuff going on. It's an important point. If you lower the temperature a little bit or increase the temperature a little bit or lower the carbon or increase the carbon a little bit, it changes a lot of stuff rapidly. So this is an important point. We call it the eutectic point. So here's a diagram of the eutectic point. This is a blow up of that single, well, the area around that single point that I showed in the last slide. So here's the eutectic point right there. And this is the upper critical temperature on the left, and this is the upper critical temperature on the right. And this is the lower critical temperature, 1333 degrees Fahrenheit. And here's a diagram of what happens if you cool down a steel with 0.4% carbon. Initially, you've got all austenite. Then you cool it down below the upper critical temperature. You've still got some austenite, but now your ferrite grains are growing and they're transforming those austenite grains into ferrite grains. Then we cool it down some more below the lower critical temperature. And now we've got ferrite grains as well as perlite grains because there was more carbon than the ferrite grains could absorb. So some of that carbon had to diffuse somewhere else. It had to migrate, had to go somewhere else. All right, and that process is slow. That's a slow process for the actual carbon atoms to physically migrate, to go somewhere else into an adjacent grain structure. That's not a rapid process. So this only really happens if you're cooling it down pretty slowly over time. All right, if you're right here at the eutectic point and you're cooling it down, first you got all austenite, and then you cool it down, and then it all turns into perlite grains. So if you're right at 0.8% carbon and you cool it down, then what you're going to have is all perlite grains. All right, and then over here, if I've got a very high, this is a very high carbon steel. If I'm cooling it down, first I start with all austenite, and then I cool it down, and I've got cementite that starts to take over the austenite grains as I cool down below the upper critical temperature. And then as I cool down below the lower critical temperature, I start to get perlite grains. So as I'm in this region right here, I've got perlite as well as cementite. Cementite has a lot more carbon. I didn't really say this before, but cementite has a lot more carbon in it than even perlite does. Right, because perlite just has those grains, those the bands of alternating bands of ferrite and cementite. All right, here's a couple more pictures of the transition. Here's what that transition looks like from all of our grains being austenite to just starting to grow some other grains. So this is a little cementite nucleus. and then it's going to start growing bands because this is going to grow into perlite. So it grows some layers of ferrite and then some additional bands of cementite. And this is happening in multiple grains at the same time. And it's just like grain formation. So your grains actually kind of regrow from the austenite material. You've got ferrite and perlite grains that actually grow from and inside the grains of austenite. And this is our final product. All I can see here are perlite grains. So we know because of that, because this evidently is all or at least mostly perlite. So this must be pretty close to a 1080 steel, something pretty close to that. All right, so that was our equilibrium phases. And equilibrium phases rely on the carbon physically moving. It's called diffusing. Diffusion is like the process where, okay, I got a coffee maker over there, and gradually the smell of the coffee diffuses into the air in the room to where I can smell the coffee over here. And if I wait long enough, maybe outside my office door, maybe somebody can smell the coffee smell out there. That's a diffusion process. Those aromatic molecules of coffee that I can smell gradually make their way into the air and they physically move. Right? Same thing with the carbon. As you're cooling it down, the ferrite grains can't hold very much carbon. So the carbon has to physically move to an adjacent grain where it can be absorbed or turned into some other material. So if you don't allow it to cool down slowly, and we're talking on the order of at least hours here is what you'd need to cool it down slowly. If you cool it down quickly by just dunking it into some water or some oil or cold air, like I mentioned before, then what's going to happen is the carbon is kind of frozen in place and the carbon can no longer diffuse because diffusion happens more readily at higher temperatures. So if you cool it down really quickly, then you're kind of stopping that diffusion process from happening. And so it's going to form something else. It's going to form some other material when the carbon is trapped there. It's going to form, as you can guess, it's going to form bainite or martensite, depending on how quickly you cool it down. I want to note that we call these metastable phases. So at room temperature, they're stable. They're not going to transform into something else, but they're only going to form when you kind of cool it down artificially quickly. So if you just kind of let it gradually cool down, these are not going to form. You have to actively do something, cool it down quickly to get these to form. So we call these metastable. So it means kind of stable. All right, so that's why they don't appear on the equilibrium diagram. Both of these, bainite and martensite, to varying degrees, both of these are very strong, but very hard and very brittle and not tough. And for most, it depends on your application. It depends on what you want to use this steel for, but most of the time, they're not desirable. Most of the time, you want, for most purposes, you want a steel that is going to be tougher and a little bit more ductile. There are exceptions, but most of the time you don't necessarily want a lot of bainite and martensite in your specimen. Let's talk about martensite first. So it's not an equilibrium phase. We talked about that. And martensite is what you get is if you cool it down really quickly, like on the order of a second or two, something on kind of that time frame. And in order to cool it down, we call that process quenching. And we're going to do that in lab 7. So like I said, the carbon becomes trapped in the material. And so it stretches and it forms these other kind of structures, which we call martensite. Martensite is a pretty complicated structure, pretty complicated lattice structure. It's called a body-centered tetragonal lattice, not a cubic lattice. It's pretty complicated. Of all the different materials, martensite is the hardest and it's the most brittle. And it's strong, but it's not tough at all. It's not tough at all. And you're going to see that when we do Lab 7. The way that people often describe martensite pictures, they say they look kind of like feathers. You know, like a feather has kind of like a stem and then little things that come off of the main stem. If you kind of look at this picture, you can kind of see, you know, maybe the main stem is right here, and you got kind of feathers that come off here and here and here and here and here. Or there's some feathers that are kind of over here in this area and this area and this area. It's harder to see in this picture right here. But they don't really look like grains, do they? They don't look like, you know, your typical ferrite grain, which is just kind of a chunk, you know, a little piece of gravel, very, very small piece of gravel, but it doesn't really look like that at all. And that's because the carbon is frozen in there and it's trapped in there, and it ends up kind of deforming the lattice and turning it into a different lattice structure altogether. So that's martensite. Bainite is a similar idea as martensite, but not quite as extreme. So you have to quench it quickly, but not quite as quickly as with martensite. So you're cooling it down, but not quite as quickly. And it kind of has properties in between martensite and perlite. It does form a BCC lattice structure, just like ferrite does. And it's hard and it's brittle and it's strong, but not quite as much as martensite. It's still not very tough. It's not a tough material. And the way that bainite usually looks, if you zoom in on it, people say that it looks like plates, like rectangular looking plates. So this is a pretty good picture right here. You can see these kind of rectangles right here. Those are a pretty good depiction of bainite. Over here, you can kind of see some of the same thing. There's some structures over here and lots of places in this picture that shows these kind of rectangles that look like rectangular plates. So that's characteristic of bainite. All right, you know what? I think this is probably a good place to stop this video. So let me go ahead and stop this video. We have covered the steel equilibrium diagram, and we've covered not only the equilibrium phases, but also the non-equilibrium phases. And we've talked about their characteristics and when they will form, what they look like, and the process by which you would get them. You know, as you're cooling them down, what phase do you get first? And then you keep on cooling it down. Then what do you get? And then at room temperature, what phases do you get? So I would expect you to, you know, be comfortable with the phase equilibrium diagram. You know, like if I gave you a blank phase equilibrium diagram, I'm not going to ask you to worry about the delta phase. Remember, that was in the upper left corner. I said don't worry about that. But aside from that, I think you should be able to fill in the regions. You should be able to fill in the region that is liquid and the region that is austenite and the region that has austenite and ferrite and the region that has ferrite and perlite and so forth. That's about the level of familiarity I would expect you to have after studying this material. All right.